Hey guys, how's it going? My name is Professor Jennifer Hill and this is Divide and Conquer Math. And this is the last video in my study series on the study practice set that helps you get prepared for a test on integration. So this video is a little bit unique from the first 4 videos in my integration series because the first 4 videos had to do a lot more with like integration problems, so straight up just calculating integrals or kind of things related to that. Now, this video has to do more with what an integral means, so we're going to be looking at trickier things like area problems and how that relates to integration, or Riemann sums, or drawing different rectangles to calculate area, things like that. That's what we're going to focus on in this video. So I think this is very different from some of the previous ones, but it should give you a nice hodgepodge of kind of other topics that can come up with integration. Now, the way that these videos work, you're going to want to look in the description and download the problem set, and then you'll notice that the problem set includes both an answer key and also references to other videos that you can watch if you realize that you need a review on one of these problems. So for the first hour, you're going to see me working on getting ready to really go through this problem set, and then after an hour I will tell you that time is up. I hope that you will grade your own work and see, what did you forget entirely, or, what ones did you not get right, and then anything that you want to see a worked out solution to, you can look in the description of this video and you will find time markers to every single problem in that problem set. And then, like I said, if you don't know how to do a particular problem, you can look in the problem set and I give you links to other videos that you can watch if you want to go back and really refresh a topic. So hopefully this is really a one-stop shop to get you organized and ready for a calculus exam. I'm super curious to know what you guys think of this video, so if you find it helpful, please consider giving it a like or leaving me a comment or hitting that subscribe button, and otherwise, let's get to it.
Hey guys, I'm going to start going through the solutions now, so if you're not done, you might want to hit pause or start the study video over again. Okay, so for the first two problems for each function, we want to create an upper, lower, and midpoint sum with four rectangles of equal width of on each given interval. So for this first problem, so we've got f of x equals x squared on the interval from 0 to 2, and I went ahead and just used desmos.com to draw a graph, so I can just kind of draw on this. So I love Desmos. If you watch this channel, you know I love this website because it just makes graphing so much easier. So what we're going to do is we're basically going to divide up, like before I actually start on this problem, problems like this where you have to do all of these sums, it's best if you get organized, okay? So what I want to do is I want to have this visual here, and I want to get myself organized because then when I have to actually do these sums, if I'm organized enough, it's very quick. So first I just think about these upper and lower sums and what do those intervals look like? So not what does the sum look like, but just what do the intervals look like? And so basically I need to divide this interval into four parts. So here's 1, 2, 3, 4. Now with an upper or lower sum, which endpoint you're going to use for the height is depending on which sum you're talking about. But again, I'm just trying to get organized here. So these green lines will indicate, you know, where either those upper or lower kind of endpoints are. And then I'm also going to have the midpoint sum. So I'll go ahead and just kind of draw that out as well. So the midpoint falls in between each one of the green lines. So that's kind of within each interval. So now what I'm going to do just to further organize myself and make my life easier is I'm going to make a table of all of these endpoints that I see for the upper and lower sum, and then also for the midpoint sums. If you take the time to do this, these problems get so much easier. I see so many students who will not take the time to do this, and they end up making a mistake. They get lost in their work. So I highly recommend that you actually spend the time doing this. So for my upper and lower sums, so this is 0, this is 0.5, this is 1, 1.5, this is 2. And then for my midpoints, so if I go through each midpoint, this is 0.25, 0.75, 1.25, 1.75. So now that I know kind of what those x coordinates are, I can figure out what the y coordinates on these are. So I just went ahead and filled in the tables. So once you have these tables, personally, I think that the rest of this problem comes together pretty quickly. So once you have these tables, I'm going to reference these again. We really have all the info that we need for this problem. And now I'm just going to walk you through like how you can approach each one of these sums. So for the upper sums, we already talked about what these intervals look like, right? So here are my four intervals. And so for the upper sum, I want to figure out how do I draw this in such a way so that my intervals are over the curve. So I want a more generous sum. So if you look at this, so I have specifically drawn this so that I am over the curve. So this is what you are looking for when you are looking to do an upper sum. So if I continue this, so notice like I have chosen the endpoints that will get me this overestimate of the curve. So that's what the upper sum is. And all we do once we figure out kind of where we want to draw kind of our heights is then we just want to figure out what's the area of each one of these rectangles. So I could literally just think of this as an area problem. However, I've made my life so much easier because I came up with this table, right? So rather than me having to kind of futz around with, oh, now I have to go through and figure out the heights, because I did this work beforehand, the rest of this comes together pretty quickly. So first I have to figure out what are the widths of my rectangle, and they're all going to be the same width. So we can just use that calculation of taking this interval and then dividing by the number of subintervals that we want. So we could probably tell this just by looking at this, but the width of each rectangle is going to be 0.5. And then for the height, so the heights, we can use this table to help us figure that out. So now that I have this table in front of me, I know like for this first rectangle, that height right there is 0.25. And then for this next one, this height is at 1. And I can use the y column here to help me kind of figure out those heights. Continuing on, this will be 2.25. And then for this last one, so up here, this one is 4. Okay, so if you compare these heights now to our table, that just so happened to be this part of the table. So I've got everything pretty nicely laid out here. So now I just have to take the width of the rectangles and then add up all the heights. So here's the way that that calculation can look. So I've got each individual height times the width, and then you just finish that, and that's 3.75. So that's it, you're done. Okay, so now that's the upper sum. So if I go to the lower sum and I do the same thing, so again I get those 4 intervals. So now I'm just looking to draw my rectangles so that now I'm below the curve. So see how I've drawn this first rectangle, so it's intentionally below the curve. So that's what you're looking for now with this lower sum. So if I go on to the next one, so again I'm below the curve, and then if I continue on, so these are all below the curve. So that's what the lower sum indicates. And then it's the same idea, right? So I still want to get to those areas. And so I can use this table once again to like kind of suss out what the areas are. So the width is still 0.5. We already did that work. And then the height, we can still use this table to help us figure that out. So like for this first height here, this is 0. Then for the next one, this will be 0.25. And then continuing on, this is 1 and 2.25. So I've got all of that information in my table, and it just so happens to be this part of the table here. So like I said, the table is a really handy way to help you kind of figure out what these heights are. And so then I can do my calculation in a very similar manner. So I've got the width times the heights, the sum of the heights, and then I can just finish that. So that comes out to 1.75. Okay, and now we can pivot to the midpoint. So the midpoint, remember we took our intervals and then we subdivided each interval by the midpoint. So that's actually these pink lines. So when we're doing a midpoint sum, we're using the midpoint to literally dictate the height. So if you look here, here's where my midpoint is. So there's the height of my rectangle. And so then I just want to continue that throughout. So I do that for the next one, and then I can do that for the other two as well. And it's the same game, right? So we're still just trying to get to the areas here. And we've already done the work to figure out the heights of these rectangles. So my width is still the same, and this table that I drew is going to help me get to my heights. So if I'm looking, if I'm trying to stay visual with this, so this first height is 0.625 and then 0.5625. So I'm literally just using this table, right? These are just the heights that I figured out from before. So now I can do that same calculation of taking my width times the sum of my height. So again, I can just, put that calculation together, and then there's my answer, so 2.625. So that is how you can organize yourself and then kind of like fly through these problems pretty quickly. So I know it seems like a lot of work to have to do that organization at first, but I think once you have that laid out, it makes the rest of this go pretty quickly. Okay, so moving on to number 2, so I've got the function 1 over x from the interval 1 to 5, and I need to make the upper, lower, and midpoint sums again. So once again, from Desmos.com, I have another graph here just to help me kind of illustrate everything. So this is 1 over x, and you can see it's from 1 to 5 here. So if I'm just looking at my upper and lower just intervals, so dividing this up into 4 intervals would look like this. And then if I wanted to get to the midpoints, so then I would just take the midpoint of each of these intervals, which would look like this. So I've got kind of all the endpoints here. So what I like to do and what I advocate for when you have a problem like this is take the time to figure out all of the x and y values in front of you and organize these into tables, because then it makes the rest of this question go so much faster, and it really organizes you and helps prevent an error. So for like my upper and lower sums, so my endpoints, I've got 1, 2, 3, 4, 5. So I'm going to figure out the y values for those. And then for my midpoints, this is 1.5, 2.5, 3.5, 4.5. So then I just take the time to take all of these values and put them into the function. And so this is going to really help accelerate the calculations that I need to do. So we have all the info that we need now, so I can now actually answer each part of this question. So starting with the upper sum, so these were the intervals, right, that I was just talking about. And so for an upper sum, what you're looking to do here is you want to draw your rectangles in such a way that they are above the curve. So however that works. So upper means you kind of have to think about it, and you might have to actually really draw the illustration to figure it out. And so then if I continue on with this, so you can see, so I'm drawing each of these rectangles in such a way so I can easily see where that upper sum is. And really what I'm trying to do now is just figure out the area of each one of those rectangles. But rather than sitting here trying to mess with, oh, what's the area of this? What's the area with this? This is where having the table is going to really accelerate our progress. So first things first, we've got to figure out what are the widths of all of these rectangles. And so that's where I can take this interval, the length of the interval divided by the 4 subintervals. So we probably could tell this just by looking at this, but I always like to show the calculation ones. So the widths of everything are 1. And then to figure out the heights of these rectangles, that's the point of having this table. So this is going to help accelerate what these widths are. So for instance, this first one, this is the height of 1. Sorry, I think I said width, I meant height. And now for this next rectangle, this height is 0.5. So I can just, choose the value off of this table. So if I continue on, so the next one is 0.33 and then the last one's 0.25. So in this particular instance, that just happens to coincide with this part of the table. So now I have all my widths and my heights, so I can set up the calculation here. So it's going to be the width times the sum of those heights, and then if I sum all that up, that comes out to 2.08. So that's my upper sum. So now pivoting to the lower sum, so I'm going to kind of go through the same routine of there are kind of all the intervals to get to my lower sum, and for a lower sum, I want to draw my rectangles so that I choose the endpoint that gets me below the curve. So notice now this is a lower sum. So I can continue that on for these other rectangles. So you can see this is definitely going to be below kind of what the actual value of this area is going to be. We can tell this is too low, but that's okay. That's what we're being asked to do. And so once again, I just want to figure out the area of these. Having that table just helps organize me. I already know what my width is. It's still 1, and then that the heights can be determined from the table. So now as I go rectangle by rectangle, the height of the first rectangle is 0.5, and then I can just continue to use the table to help me figure out these other heights, right? And so now I notice that just happens to coincide with this part of the table. So it's really dependent on the function when you're talking upper and lower sums as to how this is going to work out. So you've really got to use kind of the picture to help you with it when you're getting used to this. But now that I have everything here, I can go ahead and set up my calculation, the widths times the sum of the heights. So I get 1.28, and that's going to be my lower sum. And finally, now I've got the midpoint sum. So I take those intervals that I had before, and then I take the midpoint of each of them. So I use those midpoints now to dictate my heights. So this one is dictating the height of the first rectangle, and then the midpoint for the next one is dictating the height, and so on and so forth. And it's the same thing. We're still just trying to find the areas, but we're all organized to easily do this. So I've got now that midpoint table that I came up with. So I know that the width was 1, and my heights are still dictated by this table. So if I went through the graph now and just tried to see what's the height of each one of these rectangles, so it'd be 0.67 and then 0.4 and 0.286 and 0.22. I'm just reading these straight off the table. So once you get that organization level in, it really goes pretty quickly. And so then it's just, now I can just sum up those heights times the width, and so I get 1.576. That is my estimate for this midpoint sum. So for our next two problems, we want to write the following sums in sigma notation. So looking at this sum here, so I have really just, I'm adding up a bunch of odd numbers. So for my sigma notation, so I need to have, of course, sigma. And you can use k or you can use I. I'll use k in this case. So I want to go from k equals 1. So this will be 1, 2, 3, 4, 5, 6 terms. So I need k to go from 1 to 6. And now I just need to figure out a way to write this so that I end up getting each one of these values as I cycle through my k's. So that's going to look like then, in this case, 2k minus 1. And that really just comes from like playing around and knowing just a couple of tricks. So just a trick for you if you didn't know that. So even numbers can generally be represented by the expression 2k, and then odd numbers can be represented by the expression 2k plus 1 or 2k minus 1. So you can mess around with the plus or minus 1 depending on your sum. So if I just think about this, my goal is to plug in k and to get this sum. So if I were to work this out, let's see if I just test this real quick. So 2 times 1 minus 1, so maybe I'll just write this out. So 2 times 1 minus 1, that's 2 minus 1, so that equals 1. And then if I go to the next one, so k equals 2 now, this will be 4 minus 1, so this is 3. 2 times 3 minus 1, so this is 6 minus 1, so this is 5. And so then as I continue on with this, I can just keep checking this, I guess. So 2 times 4 minus 1, so this is, this is 8 minus 1, so this is 7. 2 times 5 minus 1 will give me 9, and then 2 times 6 minus 1 will give me 11. So you can always go through and like double check your work like that if it's a small sum, if you're not confident, but that would be your that would be the answer in this case. Okay, so for number 4, so once again I want to write this in sigma notation. So I have alternating signs here, and then I have just basically like the denominator of this fraction is being increased by 1 each time. So in this case, so let's see, I'll use I this time. Sometimes books use I, sometimes they use K, so I'll use, it doesn't really matter which letter you use. So I've got, this is my first term, second, third, fourth, fifth. So I need to go from 1 to 5. Okay, so my fraction will be 1 over I, or 1 over K, whatever letter you chose. And then I need to make sure that I have this written so that the signs alternate. So I need to multiply this expression by -1. And I need the first time I plug in 1, I need this to end up being positive. So this will be to the I plus 1. So this can be a little tricky sometimes trying to figure out like the indexing with this. So don't be afraid to actually sit down and write down some of your sequence if you're not sure. So if I try to plug this in now, so I start with I equals 1. So let's see, this becomes 1 plus 1. So this is 1 times -1 squared. So yeah, that'll give me 1. And then if I continue this, so if I move on to I equals 2, so now I'm going to have that this is 1/2 times -1 to the third. So yeah, that'll give me -1/2, and so on. So if you're not sure, just force yourself to try out the formula to make sure you've got it. For 5, 6, and 7, we're going to be evaluating sums. So starting with number 5 here, so I hope you realize like the goal of these types of problems is for you to not write this out 24 times. Sometimes I do see students do that, and that just makes you lose a lot of time on an exam. The point of a question like this is to show that you know some of the summation formulas. So I'm going to just flash up here some of the rules for sums, and you can pause the video if you need to. So a lot of times if you're being asked about sums, you do have to have formulas like this memorized. And for number 5, we're literally just plugging in this formula here, okay? So I really just need to take that formula and use it. So this was, maybe I'll just flash it up on the screen. So here's that formula. So in this case, my n is equal to 24. So here's my n. So I can just plug all of that into this. So this becomes 24 times 24 plus 1 divided by 2. So that's really the only calculation that I need to do. So the value of this is going to be equal to 300. So for number 6, so once again, so we really need to kind of flex some of the formulas that we have. So I will just flash the formulas up here of algebraic rules for sums, and you can pause the video and write these down or review them as you'd like. So for this particular sum, I need to break this up into a few pieces to make this something I can work with. So first things first, we have this part of the sum and this part of the sum. And this constant here too, I can break that out and put that in front of the sum. So what I'm going to do is I'm going to break this up into a couple sums. The 2 is going to come out in front. So I have this first sum now, k equals 1 to 200, k squared. And then I'll have this second sum, k equals 1 to 200, just adding up the constant of 3. And so now, just FYI, I use the constant multiple rule to help me break this up. And now I'm going to use the constant value rule to evaluate that last sum. And then finally, I have a sum for the first n squares, so I'm going to use also this formula here. So you can pause the video and write those down if you need to. Okay, so let's do this then. So this is going to be 2 times, and then this will be 200 times 200 plus 1 times 2 times 200 plus 1. All of this divided by 6. So this is my k squared sum. And then for this second part, so this will be minus 200 times 3. So there's all the work that's going to go into that. And when I compute all of this out, I get pretty big number here. So let's see, that comes up to 5,372,800. So for number 7, so this problem looks a little bit tricky. So I've got k times 3k minus 1, and this is, I got to sum this from 1 to 15. So one thing I want to point out in our sum rules that we have, we don't have like a multiplication rule. So we have a constant multiple rule, but I don't have something that says like if I'm taking k times another expression that I can break those up. So I'm bringing this up, and you can pause the video if you need to review the formulas. I'm bringing this up because as this is written, I cannot evaluate this, so I need to distribute this k first. So let's go ahead and do that. So this goes from 3k squared minus k. Okay, so this I can evaluate, and I can break this into 2 pieces now. So, okay, I've got those. And then the 3 here, I can break that out in front. So let's see, I've got the 3 going here, and then I've got this sum from 1 to 15, k squared, and then I'm going to break up this other sum like so. And so from here, now it's just a matter of using these formulas to finish the problem. So let's go ahead and do that. So this is going to be now 3 times, so this is k squared, so this will be times 15 times 15 plus 1 times 2 times 15 plus 1, this whole part divided by 6. And now for the second part of this, this will be 15 times 15 plus 1, all of that divided by 2. And so now it's just kind of hashing out the calculation here. So when I go through and I just calculate all of that, I get 3,600 as my final answer. So for number 8 and 9, I want to point out the directions are to only use known area formulas. So we're being asked to compute an integral, but we've been told to not use integration really, to use area formulas. And the point of these problems is to really try to get you to connect that area and integration go hand in hand. So if you have to do a problem like this without using any integration formulas, you're going to need the graph. So I've gone ahead and I drew this out. And you're basically then looking to find the area of kind of this enclosed shape in here. And in this case, this just looks like a triangle, so we don't have to overcomplicate it. We can just use the good old, formula for a triangle, 1/2 base times height. That's all we have to do. So in this case then, if I go ahead and I measure this out, so let's see, I go 1, 2, 3, 4. So 4 would be my base. And then for my height, I'm going up 1, 2. That's it. That's all I have to do. And so then this just comes out to 4. That would be my 4, I don't know, I guess units squared, right? That would be the area. Although if we're just trying to compute the value of the integral, then we can just say 4. But that's it. That's all you're really being asked to do. So you want to not go too crazy with trying to use integration formulas. If you want to back this up using an integration formula, you can, but make sure if you're being asked a problem like this is really the work that you're being asked to do. Okay, so for number 9, so remember the directions here are still the same, only using known area formulas. So I can't use integration formulas to do this problem. So what I really need to know then is, what does this graph look like? So I have the graph of 2x plus 1 right here from 0 to 4. So notice I'm going from 0 to 4. And so now what I want to think about is, what is the area of this shape from the top of the graph down to the x-axis? Now, looking at this is kind of an odd shape. I could really break this up into 2 pieces, a triangle and a rectangle, so I can calculate these 2 areas. So this is what I'm being asked to do. I am not being asked to bust out integration. I am being asked to show that I understand that this will equal whatever the area of this is. So now if I want to figure this out, so let's see, the gold triangle here, so this is 1/2 base times height. So this is a base of 1, 2, 3, 4, and this is a height of, let's see, I go up 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I go up 8. So this is going to be 1/2 times 4 times 8. So that comes out to 16. And then for my rectangle here, so I just need to take my length times my width, right? So in this case, the length is going to be 4, and then the width is going to be 1, width or height or whatever you want to call it. So I get my area then is going to be 16 plus 4, which is 20. Now, you might say, but I could have done that with an integration formula. But again, that's not what we're being asked to do. However, we probably could go through and check this, right? We could check this very easily with an integration formula. So let's forget all that. Now let's use an integration formula just to see if we get this. So if I were to integrate, this would be x squared plus x, and I need to evaluate this now from 0 to 4. So I have 4 squared plus 4 minus 0, so this is 16 plus 4, so this equals 20. That's the answer that we found, right? So the whole point of questions like this is to establish that you understand these 2 things are the same thing. You could totally use this as a check, but don't use it as the main way that you solve something if you're being asked to show your work in a certain way. So the last 3 problems are asking us to find a formula for the Riemann sum obtained by dividing the interval into n equals subintervals and using the right-hand endpoints. And then take the limit as n approaches infinity to calculate the area under the curve, and then to use the fundamental theorem of calculus part 2 to confirm your answer. So starting with number 10, so this was asking for something extremely specific. And one thing that you have to know is this general Riemann sum for right-hand endpoints. I think that this formula is a little bit easier to use than the left-hand endpoints just because it's a little bit less notation. So I prefer this formula as it is. So we need to use this to start to find that general formula for getting into the n equals subintervals, okay? So maybe the first thing that we want to do with a problem like this is just write down the formula so that it's very clear that we knew how to start this party. Even if we make a mistake after this, at least it's very clear that we kind of knew where we wanted to start. And that's a good way to like maximize the partial credit you can get on a problem like this. So there's the formula that I want to use. So now I have to kind of take all these pieces and start plugging this in. So I really just need to work this out in its entirety. So let's get this party started. So I'm going to take f. So my a in this case is going to be equal to 0, and my b in this case is equal to 2. So as I'm kind of working all of this stuff out, I can omit the 0. I can just write 2 over n times k. That's what this inside piece is going to come out to if I plug in my 0 and my 2. All of this times 2 over n. Now, I've broken these types of problems down in other videos, so if you have no idea what I'm doing, I have links to this in the description below where I really break this all down. remember the point of this video is to just walk you straight through the solution. So just a reminder on that. Okay, so now what I need to do is I need to plug in 2k, let's rewrite this, instead of writing this as 2 over n times k, I'm going to rewrite this as a 2k over n. So I'm going to plug 2k over n into my function. And then this 2 over n here, I'm actually going to just factor this out because this is not what my sum is on, right? My sum has to do with this k. So let's just go ahead and factor that out. So this will be 2 over n. Okay, so this is going to come out to then my function. I'm going to plug in 2k over n into the x squared spot. So this becomes 3 minus 2k over n squared. So here's what I need to work out now. So this is 2 over n, and then this is 3 minus 4k squared over n squared. So now looking at this, I can see that I can break this sum up into pieces. So I've got this piece here and this piece here. So I don't want to do too much too fast. So let's see, I'm going to use a square bracket to break this sum up, because remember we also have that 2n in the front. So here's the first part of the sum, and here's the second part of the sum. Okay, now in this part of the sum, what is my constant? Remember, what are we actually doing this sum on? Is it on k or is it on n? It's on the k's, right? That's indicated right down here. So I can factor out the 4 and the n squared. So we need some more space, so I'll clear some space. So now what I want to do is I'll go ahead and just factor this out. So I'm really trying to take my time. I know sometimes when you watch videos like this, it probably looks like I do this all flawlessly, like I have no issues with it. But I have to actually occasionally do multiple takes of these videos because I make a mistake. And I actually find that writing out extra levels of detail helps prevent that. So before I go any farther, I don't want to forget about this 2 over n. So I'm going to go ahead and I'm going to distribute it to each of these sums now, so that hopefully I don't forget it. I forgot it in an earlier take. So I am refilming this. So it's very easy to make a mistake with these. So you really want to find a system for yourself where you're really drawing out the details so you don't forget anything. Okay, so now we are ready to start using formulas here. So we can go ahead and here are some of the algebraic rules for sums. So we're going to use this constant value rule right here. And then we're also going to take this summing the first n squares. So you can pause the video if you need to write those down. So I'm literally just going to apply those formulas now. So now I have 2 over n times 3 times n, and then I have 8n cubed, and this part right here I can replace with that formula. N, let's see, n times n plus 1 times 2n plus 1, all of this over 6. So you might look at this and say, oh, I could do so much of this in my head. So the thing about doing stuff in your head when you have this much going on, that is just laying the groundwork to make a very simple mistake. That's actually what happened to me as I was filming some of these. So you really, really want to slow your brain down as you're working through this. So like now I can see I can cancel out these n's, and then this n cubed can become n squared. I can cancel out this. And let's see, I can also divide the top and bottom here by 2, so this will become 4 over 3. So let's rewrite this line. So now I've got 6 minus 4 times n plus 1 times 2n plus 1 over 3n squared. Okay, so I'm not done. I have to continue working out the top here. So let's clear some space. All right, so now let's see, let's FOIL out the top and multiply it all together. So this comes out to 2n squared plus 3n plus 1. And now I'm going to distribute in the 4. So I have 8n squared, let's see, plus 12n plus 4 over 3n squared. Okay, so be careful with this minus right here. So I'm now going to break up this fraction, and I need to distribute this minus to the whole thing. So I'm actually going to just put in a set of square brackets here so I don't forget. So this becomes 6 minus, so this is 8n squared over 3n squared, 12n over 3n squared, and 4 over 3n squared. And so now I can go ahead and simplify this. So we're almost good here. So this is 6 minus 8 over 3. Now don't forget to distribute the negative sign. Minus 4 over n minus 4 over n squared. And so now I can combine this 6 minus 8/3. So remember, 6, I can rewrite 6 as 18 over 3. So this will become 10 over 3 minus 4 over n minus 4 over n squared. So this was the first part of the problem of finding a formula for the Riemann sum by dividing this into n subintervals and using right-hand endpoints. That's the first part of this problem. So this would be the formula. Okay, so next, now we want to go through and take the limit as n goes to infinity. So let's clear some space. Okay, so now I'm going to take the limit as n goes to infinity of this entire expression. And let's see, oops, this was actually over 3n squared, sorry, 3n squared. I dropped that 3 earlier. It doesn't matter for the final answer here, but so these parts are both going to go to 0. And now my answer is just going to be the limit as n goes to infinity. This is 10 over 3. And so that is equal to 3.33 as a decimal. Okay, so the whole point of this is to get you to connect area, Riemann sums, and integration. So this represents that process of taking an infinite amount of rectangles, and then summing up the area. And this is what that area would be. But the whole thing about this is that the fundamental theorem of calculus, the second part, makes it so that we don't have to go through this painful process. So this is what you used to do before we had integration. And now let's take a look at what happens when you have integration. So now I'm going to use the fundamental theorem here, and it's going to go so much faster than all that other work that we did. So I'm going to go from 0 to 2, 3 minus x squared. So all I have to do now is integrate. So if I integrate this, this is 3x minus 1/3 x squared, and, oops, sorry, x cubed. And I evaluate this from 0 to 2. So if I plug this in, I have 3 times 2 minus 1/3 times 2 cubed, all of that minus 0. So that's 6 minus 8/3. Doesn't that look familiar? So that's going to be 18 over 3 minus 8 over 3. So our answer is 10 over 3. That's exactly what we found before, but we can check this with integration. So this is a great check to do if you have to do a Riemann sum. Even if you're not told to use the fundamental theorem of calculus, you can use this as a check. Okay, so for this problem, so same direction as before, we need to find a Riemann sum. Let's see, I'll just show the directions. Find a formula for the Riemann sum obtained by dividing the interval to n equals subintervals, and then use the right-hand endpoints. And then we take that formula, we take the limit as n goes to infinity, and then we use the fundamental theorem of calculus to check our answer. So I've broken this formula down in other videos, so if you have no idea what this is or how to use this, you can look in the description below. I have lots of videos where I break this down in great detail. I'm just going to go ahead and use this. So I always say, you know, when you're working on something like this on an exam, that you want to start by first just repeating the formula, like that big monster formula, so that it's really clear you knew kind of how to get the party started. Because if something goes awry after this, at least it's very clear you knew what this formula was. And so now in this case, so my a is 0 and my b is 2. So I want to simplify this expression with the 2 and the 0 plugged in. So if I simplify, this will become f of 2k over n, and then this will be 2 over n. And so now I can go ahead and plug 2k over n into this expression here. So notice I have an x here and an x here, so I'm going to plug this 2k over n in twice. So let's go ahead and do that. So this will now be, let's see, this will be 2 times 2k over n plus 2k over n cubed. So I have all of that, and then I have this 2 over n. Now, if you watched my other explanation, so one thing I went ahead and did, remember this whole sum has to do with the k's. So when we look at these n's, it gets very overwhelming to look at this, but these n's, we can really just treat them as constants. So this guy right here, this 2 over n, that can just get factored out at the front. So let's go ahead and do that, and then we can just work on sorting all this stuff out for now, okay? So if I simplify, now I've got 4k over n plus 8k cubed over n cubed. Okay, and so now I want to continue to simplify this sum. So let's break this sum into 2 pieces. Okay, so I've got this 2 over n out front. Let me make this square bracket. So I'm going to break this into 2 separate sums. So this is 4k over n, and then this other sum is 8k cubed over n cubed. All right, so now let's clear some space. Okay, so now we want to simplify these sums a little bit more. So remember, these sums are all about k. So the 4, the n, the 8, the n cubed, those are really all constants. So what I want to do is I want to factor like this 4 and this n and this 8 and this n cubed out so that I can isolate the k's. And this 2n in the front is kind of making me nervous, so we're going to deal with that next, because as I've mentioned in the other problem, I have made recording errors before because of those darn constants at the front. So I'm very nervous about that. So what I want to do next, before I go any farther, I don't want to forget about this. Let's see. So I'm going to distribute this to those 2 parts there. So now I've got 8 over n squared times this sum. And then I have the other one, so this will be 16 over n to the 4th times this sum. Okay, and so now I have this really broken down and in the form that I'd want it in. So I can apply these formulas here. So I need this formula and this formula, and I can just pull them straight out. So now I have 8 over n squared, and if I replace with that first formula, this is n times n plus 1 over 2, and then this is 16 over n to the 4th times n plus 1 over 2 squared. So now we have a whole bunch of work to do to simplify this, so let's clear some space. So let's just continue to simplify slowly here. So if I keep going, I have 8n times n plus 1 over 2n squared for this first fraction, and then for this second fraction, I want to go ahead and just square all these parts. So this becomes n squared times n plus 1 squared over 4, and now I can make a few simplifications. Oops, and this should have been to the 4th, sorry. To the 4th. Sorry. Okay, so now let's go ahead and make a few simplifications. So here, this n will cancel out entirely, and then this 2 will become a 1. And then this 2 will cancel out with this 8, so I am just left with a 4 on top. So let me just start with this first fraction here. So I'm left with 4 times n plus 1 over n, okay? And then for this second fraction, so this 4 will cancel into the 16, so the 16 will just turn into 4. this n squared will drop out entirely, and then I can subtract 2 from this exponent. So now I'm left with 4 times n plus 1 squared over n squared. And what I want to do is I want to go ahead and multiply this n plus 1 squared, so I don't want to take up more space and have to write out more lines. So let me erase this. Let's write out what n plus 1 squared is. So this is n squared plus 2n plus 1. So now I can keep going with this problem. So now I have 4n plus 4 over n and 4n squared plus 8n plus 4 over n squared. So now this is what I need to simplify, so let's clear some space. So let's break these fractions up into separate fractions. So I want to just break this all the way down. So this is over n squared, this is 8n over n squared, and 4 over n squared. Okay, so now if I simplify this as far as I can, I have 4 plus 4 over n plus 4 plus 8 over n plus 4 over n squared. So my formula for the Riemann sum is 8 plus 12 over n plus 4 over n squared. So this is that formula we were looking for, as you know, we break it into n subintervals. So this is that general formula we were looking for. So now what I want to do, continuing on, just to remind you of the directions. This was the first part, okay, finding that formula. Now we want to take the limit as n goes to infinity, and that will get us the area under the curve. So if I come back to this, if I just take the limit, let's see, I can write it just over here. Let's see, the limit as n approaches infinity of this whole thing. So what ends up happening is these two parts just end up going to 0. So the value of my limit is just 8. So now what I want to do, this is like the old way of finding area, right? It's a very long, cumbersome process. And the whole reason we're going to use the fundamental theorem of calculus now is to check our work. So let's pivot. And I want to see if I get the same answer with integration, which I should. So if I take that interval, if I go from 0 to 2, and then I just integrate this function, I should get the same answer. This is literally a check to see if you did it right. So integrating this, I get x squared plus 1/4 x to the 4th. So I need to evaluate this from my limits of integration. So if I plug in this 2, let's see, I will get 4 plus 16 over 4, so that's 4 plus 4, so that equals 8. So yes, I did find the right answer. So that's the whole point of checking that. Like, the fundamental theorem of calculus part 2 makes our lives so that we no longer have to use Riemann sums. That's kind of the whole point. And so that brings us to the end of this video, guys. I hope that this was helpful for you. This is the last video in this series. This has been a very long project for me. So consider leaving this video a like or a thumbs up or subscribing to the channel. And thanks for watching, guys. I hope I catch you next time.